In this video, we're going to look at the throttling process, and we're going to look at throttling valves. The throttling valve usually will reduce the pressure, and you'll have high pressure coming in, going down to low pressure. It could be through a valve, maybe an adjustable valve, or perhaps through a porous ring of some kind. The pressure is high here, and it gets lower here, so it produces a pressure drop. Again, if we look at the first law for a throttling valve, generally the throttling process happens in a very short distance. So usually there's not enough time for much heat transfer. So usually we can assume that there's no heat transfer. Also, there's going to be no work done in the process here. As you can see, nothing is stirring anything, or nothing is moving any boundaries or anything like that. And now, it is true that usually there's a big change in the velocity. Usually the velocities increase quite a bit, but as it works out, that can usually be ignored. And so the kinetic energy change can be ignored. And obviously, there's would be no change in elevation, so the potential energy can be difference in potential energy can be ignored. So we end up having m dot times delta H equals 0 is all we have left. Of course, then we can, the mass flow rate's not going to be 0, so we can divide by that. So we end up having H2 minus H1 is 0. And so we have H2 equal to H1. So for a throttling valve, we will have this. And so we can use this anytime we have a throttling valve, that the enthalpies do not change. Sometimes they call this process an isenthalpic process. Next, let's take a look at this example. Refrigerant 134A enters a pipe as a saturated liquid at 0.6 MPa. It is then throttled to 0.2 MPa. Find the temperature change in the final state of the refrigerant. As we mentioned before, for a throttling valve, we can assume that there's no change in enthalpy. So we have H2 equal to H1. And so all we need is the inlet enthalpy and the outlet. Again, the inlet is 0.6 MPa, and we know it's a saturated liquid. And the outlet is at 0.2 MPa. And so we can look some of these values up in the table. In my book, which is Kaminsky and Jensen, that is table for refrigerant 134 is table A15. And if we want 0.6 MPa, it's over here. I have to focus it a little. And 0.6 MPa again, it is saturated liquid. Our enthalpy is going to be HF, which is 79.48. Again, in my book, table A16, H1, of course, it's going to be HF, 79.48 kilojoules per kilogram, like this. Now we know that H2 is going to be equal to H1. So it's also going to be that 79.48. And so we have to look these up in the table. And so we'll start with the saturation, again, the saturated refrigerant 134, and look up 0.2 MPa. And for 0.2 MPa, we'll check the enthalpy, see where that 79 falls. And it looks like it falls somewhere between 36.84 and 241.3. So that means it is a saturated mixture. And we can find the quality. And then also we can read the temperature right off there. Since we determined it did fall in that range, we can read the temperature right off there for 0.2 MPa. The temperature is negative 10.09 degrees C. And then we can calculate quality in the usual way. So I looked up my values on that same row, or F, and the difference between Hg and Hf, and got these values. And when you put that into your calculator, it's about 0.21. So then again, the temperature change, it started out over here at 0.6, and at that inlet, if you look on the saturation table, the temperature was 21.58 degrees C. Like I say, we found this here. So the temperature difference, it went from those values. Let me put that in my calculator. And that's 31.67 degrees C was the temperature difference. The outlet minus the inlet. And the final state, saturated mixture with a quality of 0.21. So let's take a look at this problem. Air is throttled from 100 psi to 300 psi. Find the change in temperature. Now this one's kind of interesting. Again, remember H2 is equal to H1 for a throttling process. But air is an ideal gas. And then for an ideal gas, the change in enthalpy is going to be Cp delta T. But now notice, of course, since H2 is equal to H1, this is going to be 0. And if we And CP, of course, is going to be non-zero, so then we can divide through CP by CP. So then we're going to have delta T is equal to zero. So for an ideal gas, there is no temperature change during a throttling process. So keep that in mind.